Right at the very heart of logic and computer science, there's a problem so deep it can literally create paradoxes out of nothing. But what if the solution wasn't some complicated patch, but something, well, beautifully elegant? That's what we're going to explore today with a concept called universes in type theory. It's how we learn to tame infinity.
So it all kicks off with a question that sounds pretty simple, almost philosophical. Can we create one single container, one type, that holds every other possible type inside of it? I mean, it seems like a useful idea, right? Well, as it turns out, it's a total trap.
Because that one little question leads us straight into a classic logical vortex, the problem of self-reference. It's a kind of knot in logic that has tied up mathematicians for over a century. So, how does this one simple idea manage to break, well, everything? This brings us to a super famous brain twister known as Russell's paradox. Just think about this for a second. Imagine you have a set, and its definition is the set of all sets that do not contain themselves. Okay, now for the killer question. Does this set contain itself? Well, if it does, it violates its own rule. But if it doesn't, then by definition, it should be in the set. See? It's a contradiction either way you look at it. It's a logical impossibility. So what do we even mean when we say type here? Honestly, you can just think of it as a label for a category of things. The number 5, its type is integer. The word hello, its type is string. Types just bring order to the world and stop us from doing silly things, like, trying to multiply a number by a sentence. And here's the thing, it turns out that trying to create a type of all types lands us in the exact same self-referential paradox. The system literally can't decide if this ultimate type should contain itself or not, and the whole thing just breaks down. So a single all-encompassing type, it simply cannot exist in a system that makes any kind of sense.
So how do we fix this? If one giant box for everything doesn't work, we get clever. We build an infinite ladder of them instead. And this is the brilliant core idea behind what's called the universe hierarchy.
So, how do we build this ladder? Okay, we start at the very bottom, on the ground floor, with a universe we call type 0. This holds all of our simple, basic types, your booleans, your integers. Then we build the next level up, type 1, and its whole job is to be a container that holds type 0. After that comes type 2, which exists to contain type 1. You see the pattern, right? Each new universe is just there to hold the one that came before it, and this ladder just keeps on going, up and up forever.
And just like that, the paradox vanishes. By creating this infinite hierarchy, no universe ever tries to contain itself. It only contains the universe from the level directly below it. So type 0 lives inside type 1. Type 1 lives inside type 2. That whole problem of self-reference, it's gone. The system stays perfectly consistent.
But we're not quite done. There's one more little refinement we need to make this ladder truly useful. Because a super strict separation between all the levels, well, it can be a little too rigid for doing real-world stuff, like programming and proofs. We could build what's called a strict hierarchy, where a type like integer would only ever exist on that ground floor in type 0. But a much more powerful and flexible way to do it is with a cumulative hierarchy. The idea here is that if something exists in a lower universe, it's automatically included in every single universe above it. It's like everything gets inherited upwards. The rule is really simple. Anything that has the type I is also considered to have the type I plus 1. This property, cumulativity, is the key that lets all the different levels of our ladder talk to each other and interact smoothly. And that interaction, as we're about to see, is where the real power comes from.
So, why did we go through all this trouble, building this cumulative, infinite ladder of types? Because what it unlocks is basically one of the holy grails of programming and logic. Incredibly powerful, super safe, and totally reusable code.
The key concept this whole thing enables is called universe polymorphism. I know, it sounds a little intimidating, but poly just means many. So all it is the ability to write one single function that can work across many different universe levels. It can handle types of different complexities, and you don't even have to tell it which level to work on.
And this is the big payoff. It means you can define a function, let's say one that creates a pair of two types, and it will just work, whether you feed it simple integers from type 0 or some incredibly complex mathematical structure living way, way up in type 10. You write it once, and it works everywhere. That's a game changer.
Now, this isn't just some abstract curiosity for a textbook. This entire structure is the invisible engine running behind some of the most advanced software tools that mathematicians and computer scientists use today.
So why does this matter so much in the real world? Well, it's the absolute bedrock of modern proof assistants like Coq and Agda, tools that let mathematicians verify incredibly complex theorems with computer precision. It's the key that unlocks cutting-edge fields like homotopy-type theory. And really, at the end of the day, it provides a consistent, solid foundation for both math and code, letting us build powerful, reusable tools without ever fearing those paradoxes we started with.
So think about that journey for a second. We started with a simple question that led to a paradox that breaks logic. The solution wasn't one giant box, but an elegant, infinite ladder. And that ladder didn't just fix the problem. It gave us powerful new tools for building safer, more flexible code. Which leaves us with one last big question. If this elegant structure solved a century-old paradox, what new structures and ideas are just waiting to be built on top of it?